we're going to explore what might be one of the very first composite materials ever engineered by humans. And in doing so, we're going to explore this kind of parallel history of technology. It's one that really challenges the way we usually think about human innovation. You know, we all learn this timeline in school, right? The Stone Age, the Bronze Age, the Iron Age. It's a story all about pure monolithic materials. But what if that framework, that whole story, actually hides a much more sophisticated history of development? A kind of secret history that's been running alongside it the entire time. So think about it like this. On one hand, you've got that familiar story, finding one single substance and figuring out how to purify it. You know, stone, bronze, iron. But on the other hand, there's this totally different kind of genius. The art of combining materials to create something fundamentally new, something way better. And that is the story of composites. The key word here, really, is synergy. It's this idea that you can take two totally different things, combine them, and get a third thing, a new substance with properties that are just so much better than its individual parts. It's a core principle of engineering, and you know what? Our ancestors, they got it. They understood it intuitively. Okay, and that brings us right to our main subject. We are going to dive deep and analyze what might just be the first truly engineered structural composite. And you'll find this amazing technology in the walls of some of the earliest human homes. Yeah, we're talking about Wattle and Daub. Now, I know what you're thinking. Sticks in mud, right? It's so easy to just dismiss it as primitive. But trust me, that is a huge mistake. Because when you actually look closely, when you do a real mechanical analysis, you find this incredibly elegant and sophisticated engineering solution. So, at its very core, it's a two-part system that's all about balancing forces. You've got the wattle, which is kind of like the flexible skeleton, and then you have the daub, which provides the compressive muscle. Let's break down exactly how each of these parts works its magic. All right, first up, the wattle. Think of this as the internal framework. It's what gives the whole wall its amazing ability to bend and flex without just snapping. And the material choices here, they were absolutely deliberate. This wasn't random. They used strong, vertical hardwoods like oak for the main posts, and then wove flexible saplings in between them. This created this amazing mesh designed to handle tensile forces, you know, like the wind pushing on a wall. It is, no joke, the ancient equivalent of the steel rebar we use to reinforce concrete today. It's brilliant. And that weave, it wasn't just for looks, not at all. Its complex, textured surface was a super critical design feature. It created this powerful mechanical lock with the daub. It made sure that mud mixture would just grab on and not let go, forcing the two parts to act like one single unified material. Okay, so that's the skeleton. Now for the second part, the daub. And let me be clear, this is not just mud. It's a carefully formulated recipe, a matrix that wraps around the skeleton, giving it strength, insulation, and protection from the weather. You know, the daub itself was actually a composite in its own right. It was a very precise recipe. Clay, sure, but also sand to help prevent cracking, and organic fibers like straw. But there was often a secret ingredient, something that transformed it from just plain mud into a seriously high-performance binder. And that secret ingredient? It was lime. Modern chemical analysis shows that these ancient builders would often add lime to the mix. And this kicks off something called a pozzolanic reaction with the clay. What does that mean? Well, this chemical process literally turned the mud into a kind of primitive, water-resistant cement. I mean, it made it incredibly durable. So what about the straw then? What was that for? Well, this is another stroke of pure genius. See, as the daub dries out, it shrinks, and tiny little cracks start to form. It's just what happens. But the moment one of those cracks hits a piece of straw, that fiber dissipates the energy, and bam, it stops the crack dead in its tracks. The fibers are acting as crack arresters, and that is the exact same principle we use in modern fiberglass today. It's incredible. But hold on, the system still wasn't totally complete. There was one final piece to this puzzle, the outer skin. And it had to perform a very, very specific and crucial job. And this is actually a lesson that modern building science has had to relearn the hard way. See, if you were to slap a modern impermeable paint on this wall, it would trap moisture inside. The clay would get soggy and the wooden wattle would just rot away. But ancient builders knew better. They used a breathable lime plaster. It was smart enough to block rain from getting in, but it also let water vapor from inside escape. It kept the whole system perfectly dry and stable. So, okay, when you put all of these pieces together, it's pretty clear, right? Wattle Daub isn't just some old, primitive building method. No way. It's a foundational moment in this long, unbroken story of engineering. I mean, you can draw a direct line from the principles we see in these ancient walls to the incredible power of the Mongol composite bow, made of horn and sinew. Fast forward to the critical fiberglass radar domes of World War II, and bring it all the way to the carbon fiber composites that make up today's spacecraft and jetliners. The materials change, of course, but that core idea, combining things to make something better, it's exactly the same. You know that classic image, right? Ancient builders out in the sun mixing straw into mud? It just seems so basic, like they're just adding some filler to bulk it up. But what if I told you that simple act was actually an incredible piece of engineering, one that hides a really deep understanding of both physics and chemistry? So that's the big question, isn't it? Why bother adding straw to mud at all? Was it just a filler, or was it some kind of ancient engineering secret? People knew for thousands of years that it worked, that it made bricks stronger. But how it worked? Well, that's where things get really amazing. It's a story of some very clever physics and, believe it or not, some pretty surprising chemistry. Okay, so before we can really appreciate the genius of the solution, we have to understand the problem they were up against. And if you're building with plain old sun-dried mud, you have one huge enemy: cracks. Not just little cracks, but huge, catastrophic ones. And here's the thing about mud, it's kind of paradoxical. If you push down on it, that's compression, it's incredibly strong. It can hold up massive walls, no problem. But the moment you try to pull it apart, what we call tensile strength, it has almost nothing. It just crumbles. And that one weakness, that's its fatal flaw. So picture this. You've just made a perfect mud brick, and you leave it out to dry in the sun. The surface, right, it starts to dry and shrink almost immediately. But the inside, the core, is still wet and expanded. This creates a massive tug of war inside the brick. The shrinking surface is being pulled apart by the swollen core. And what starts as one tiny little fissure can rip right through the brick, making the whole thing completely useless. So how in the world did ancient builders get around this fundamental problem? Well, they fought back with a physical fix that was just so simple but so incredibly clever. What they did was essentially invent what we now call micro-reinforcement. I mean, think about the steel rebar we put inside concrete today to make it stronger. This is the exact same idea, just on a tiny, tiny scale. They were mixing in countless little fibers of straw to create this kind of internal skeleton for the mud. Yeah, the fibers literally stitch the clay together. It's like creating this tangled, three-dimensional web that runs all through the brick. And that network just physically holds everything in place. It stops those big, fatal cracks from ever even getting a chance to start. And this isn't a small change. It completely transforms the material. The straw does way more than just stop cracks. It gives the normally brittle mud something amazing: flexibility, or what engineers call ductility. You see, a plain mud brick under stress will just shatter, boom, without any warning. But a brick with straw in it, it'll actually bend and warp a little first. It gives you a warning sign before it fails. And for building safety, that is a massive, revolutionary leap forward. Okay, but here's where the story gets even more impressive, because the ancient builders knew it wasn't just a matter of, tossing in a handful of straw. No, they had figured out the perfect recipe. And get this, modern material science has actually tested this and confirmed what they knew. The absolute sweet spot, the optimal amount of straw, is just 1 to 1.5% of the brick's total weight. I mean, just stop and think about that for a second. They figured out that incredibly precise ratio with no modern equipment, just generations of trial and error. And that number is so critical. It's like a Goldilocks situation. If you add too little straw, the brick is still brittle, but if you go overboard and add too much, the straw just clumps up and actually creates new weak spots. They had to find that perfect little window, that peak performance zone, to get a brick that was both strong and flexible. So you gotta understand, this was not a lucky guess. This was the result of generations of careful observation of refinement. It was real empirical science passed down from one builder to the next, all in the quest to create this perfectly tuned composite material. But hold on. Because as amazing as all that physical stuff is, it's only half the story. The real magic, the true genius of this whole technique is a hidden chemical reaction, one they probably didn't understand in a modern sense, but one they had absolutely mastered. Think about it. What if adding inorganic material, something that was once alive like straw, did more than just act like rebar? What if it actually kicked off a biological process that fundamentally changed the chemistry of the mud itself? Well, that is exactly what happens. As that straw sits there in the wet mud, maybe for days, getting mixed and treaded on, it starts to break down. It ferments. And this process of, biological decay, it releases this whole cocktail of powerful organic compounds right into the mud. And the star of this little chemical show is something called humic acid. Now, the technical term is a deflocculant, which sounds super complicated, I know. But what it does is just pure chemical elegance. It literally changes the clay on a molecular level. Okay, so let's zoom way in, down to the particle level. Normally, little bits of clay and water just want to clump together. But this humic acid comes along and gives each tiny particle a small negative electrical charge. And what happens when you put two negative ends of a magnet together? They push apart. It's the same thing here. The clay particles start to repel each other, forcing them to spread out perfectly and evenly all through the mix. And this little chemical trick has these amazing knock-on effects. First, the mud becomes way more workable, more plastic, just easier to shape. But the biggest thing, you need less water to make it moldable. And if you have less water to begin with, that means less shrinkage as it dries, which means fewer cracks. And as if that's not enough, other compounds from the straw act like natural glues, binding everything together even tighter as it dries. So here's the big takeaway. The thing to remember, that ancient mud brick, it wasn't just mud and straw mixed together. It was a true biocomposite, a really sophisticated material where the straw wasn't just a physical reinforcement. It was an active ingredient that was improving the actual chemistry of the mud while the brick was being made.
Today, we're going to take a deep dive into an absolute marvel of pre-industrial engineering. And no, I'm not talking about a cathedral or a castle. I'm talking about a weapon that literally reshaped the world, the Mongol Composite Bow. We're going to explore how this incredible biomechanical engine, born from the Eurasian steppe, actually worked.
And that right there brings us to the central challenge, the one question that really drove this whole innovation. How in the world do you build a weapon that can dominate from horseback? A weapon with unbelievable power and precision when your environment gives you basically nothing to work with. That is the core problem the Mongols had to solve.
If you were in medieval England, you had these dense forests packed with yew trees, which were perfect for making longbows. But the vast open plains of the Eurasian steppe, that's a completely different story. The environment itself forced Mongol artisans to get creative, to innovate, and to look not at trees, but at the resources that were all around them.
So here's the problem in a nutshell. You have no big, single pieces of wood that are good for making a powerful bow. But at the same time, steppe warfare demanded a weapon that was compact enough to use on a horse, but was still incredibly powerful. The solution was genius. They just stopped looking for wood and turned to their most valuable resource, their animal herds.
Okay, this is where the engineering gets really, really cool. The Mongol bow isn't just one piece of wood, it's a composite structure. Think of it like a carefully engineered sandwich of 3 different biological materials. Each one was chosen for a very specific job, and they were all laminated together to create something way, way more powerful than its individual parts.
And yeah, just to make sure we're on the same page, a composite is exactly that. It's when you take different substances and combine them to make a brand new material that has way better properties. Think of carbon fiber or fiberglass today. The Mongols were mastering this exact principle with natural materials centuries and centuries ago.
All right, so right in the middle of this sandwich, you've got a thin strip of wood or maybe bamboo. But here's the twist. Its job isn't what you'd think. It's not the main source of the bow's power. Instead, it's what engineers would call a dimensionally stable chassis. It's basically a neutral frame that gives the bow its shape and keeps the 2 powerhouse layers separated.
Now let's look at the side of the bow that faces the archer. We call that the belly. When an archer pulls that string back, this side is getting squeezed together with an absolutely immense amount of force. It's under incredible pressure. A simple piece of wood would just crush or buckle.
So, to handle all that compression, the artisans glued strips of horn to the belly. Horn is mostly keratin, a natural polymer, and it has two almost magical properties for this job. First, it has phenomenal strength when you try to squeeze it, and second, it has a high coefficient of restitution. Now that's just a fancy way of saying it can be compressed like crazy and it'll spring right back to its original shape instantly without losing any energy.
Okay, so on the opposite side, the back of the bow, which faces the target, you've got the exact opposite force at play: tension. When the bow is drawn, this side is being stretched to its absolute limit. So you need a material that can handle all that stretching without snapping.
And the solution for that was sinew. It comes from animal tendons, and it's almost pure collagen, which is basically nature's own high tensile fiber. When they processed it and glued it to the bow's back, it acted like a whole bunch of powerful biological rubber bands that could stretch and then snap back with just devastating force. And when you see it all laid out like this, it just clicks, right? You've got the wood core giving it shape, the horn belly on the inside resisting compression, and the sinew back on the outside withstanding all that tension. Each layer does one job, and it does it perfectly. And together, they create this biomechanical engine for storing and releasing energy with terrifying efficiency.
But you know, the real genius here wasn't just in the materials. It was in the wild, radical geometry that those materials made possible. The very shape of the bow, well, that's where the design gets truly mind-bending.
Just take a look at this comparison. An unstrung English longbow is, well, it's pretty much a straight stick. But an unstrung Mongol bow, it's a deep C shape, and it's curved away from the archer. I mean, it looks backwards. This is called a reflex, and it is the secret to the bow's incredible power.
So just think about what that means for a second. Just to get the string on the bow, the archer has to literally fight it, bending the limbs in the total opposite direction of their natural curve. What that does is preload the entire system. Before you even touch an arrow, the sinew on the back is already stretched tight, and the horn on the belly is already under compression. The bow is a coiled spring, just humming with potential energy.
But, of course, a system that's under that much tension creates a whole new set of problems. Like, how do you even manage all that power? And how do you make sure the weapon doesn't just explode in your hands? Well, this is where two unsung heroes come into play: the levers at the tips and the glue that holds the whole shebang together. So, the stiff tips of the bow, the parts that don't bend, are called sea-eyes, and they acted as levers. As the string was pulled back, the sea-eyes gave the archer a mechanical advantage. It's like a little cheat code that made the draw smoother and allowed the archer to manage the bow's immense power with way more control. And we are talking about immense power. A lot of these bows had draw weights of over 100 pounds. Thanks to this amazing composite design and the leverage from the sea-eyes, a Mongol warrior could wield the power of a giant infantry weapon, all from the back of a galloping horse. It's just incredible. Now put yourself there. Imagine you're in the heat of battle. You're pulling back this 100-pound engine of destruction. What's the one thing you need to trust completely? The glue. Because if those layers were to separate, to delaminate, the result would be catastrophic and almost certainly fatal.
So they couldn't just use any old glue. They used a very specific, very special adhesive, fish glue, made from the swim bladder's sturgeon. Now, unlike regular hide glue, this stuff had amazing elasticity. It could flex and bend with the bow again and again without cracking, all while maintaining a bond that was, get this, literally stronger than the wood, horn, and sinew it was holding together.
So, okay, you've got the materials, you've got the design, you've got the superglue, but actually building one of these things was an exercise in extreme patience and skill. It was a process that was really, when you think about it, a primitive form of polymer curing.
I mean, just look at this timeline. This wasn't a weekend project. The whole process could take a year, sometimes even more. The sinew, especially, had to be applied in super thin layers, with weeks of drying time between each one. This slow, careful curing process was the only way to let the glue fully sink into the fibers, creating a single, totally unified biocomposite structure.
So when you put it all together, the clever response to the environment, the mastery of composite materials, the genius of that reflex shape, and the incredible patience of the craft, you end up here. The Mongol bow wasn't just a weapon. It was, arguably, the most sophisticated piece of mechanical technology of its time. Period.
All right, let's talk about plywood. When you think of plywood, what comes to mind? Probably a hardware store, right? Construction sites, maybe that flat pack furniture you just put together? It just feels modern, a product of our industrial age. But what if I told you that whole idea is completely wrong?
What if the story of this humble engineered wood actually kicked off more than 4,500 years ago, right there along the Nile River? Well, that's exactly where we're headed today.
You know, most of us mentally file plywood away as a 20th century thing, and it seems to fit, doesn't it? But the actual archaeological evidence tells a totally different story, one that basically rewrites a little piece of engineering history.
So, to get how this invention even happened, you have to understand the problem the ancient Egyptians were up against. They were dealing with what you might call a geometry of scarcity. See, they had tons of stone and mud, but they had a serious shortage of one key resource: good quality wood.
The Egyptians had a really stark choice. On one hand, you had the local stuff, like acacia wood, but was knotty, irregular, just awful for making big, flat, stable pieces for furniture or, sarcophagi. Then, on the other hand, you had the good stuff, beautiful, straight-grained cedar. But that had to be imported all the way from Lebanon, which made it insanely expensive, a total luxury for royalty. So, what do you do?
Well, faced with this challenge, they didn't just make do, they innovated. Egyptian carpenters came up with a solution so incredibly advanced that it predates what we call plywood by over 4,000 years.
And the proof for this? It comes from one of the most famous archaeological sites on the planet, the Step Pyramid Complex at Saqqara. And this wasn't some minor little find. No, this was a discovery that totally challenged what we thought we knew about ancient tech. Get this, the artifact they found there dates all the way back to the 3rd dynasty, around 2600 BCE. Just let that sink in for a second. That's over 4,500 years ago. We're talking about the early days of the Old Kingdom, the era when the very first pyramids were being built.
So what was this incredible artifact? It was a piece of a sarcophagus, a coffin. But when researchers looked closely, they realized it wasn't a solid piece of wood at all. It was a composite panel. It was actually built from 6 separate layers of wood veneer, and each layer was sliced to just 4 millimeters thick. This was engineered wood.
But here's where the story goes from just being clever to absolutely brilliant. It wasn't just that they layered the wood, it was how they did it. They used the single most important principle of modern plywood, a deep engineering insight called cross-graining.
The idea is actually incredibly simple, but it is so powerful. You lay down one thin sheet of wood with the grain running in one direction, and then you stick the next sheet on top with the grain running at a 90-degree angle to the first. Then you just keep repeating that pattern. And this wasn't for looks, this was pure structural engineering.
So why do this? Well, it solves a huge problem with wood. Wood is what scientists call anisotropic. That's just a fancy way of saying its properties aren't the same in every direction. It's super strong along the grain, but it's much weaker and way more unstable across the grain. It loves to expand, shrink, and warp whenever the humidity changes.
By turning those grains against each other, the Egyptians created a kind of mechanical lock. The natural urge of one layer to expand or shrink is physically blocked by the strength of the layer right next to it. They're basically forcing each other to stay put. Each layer stabilizes the next.
And the result of this process was absolutely revolutionary. They took this unstable anisotropic material and they turned it into a stable isotropic one. The final board was strong and stable in all directions. It wouldn't warp, it wouldn't twist, and it wouldn't split. They had literally engineered the weakness right out of the wood.
What makes this whole thing even more mind-blowing is the level of skill it took. You have to remember they were doing all of this without a single power tool. This was all achieved by hand with the incredible skill of ancient carpenters.
I mean, just look at the tools they were working with. They were using copper saws, and copper is a pretty soft metal, so they would have had to sharpen them constantly. To even get the saw to cut, they had to pour abrasive sand into the cut to help it grind away the wood. And then, to hold it all together, they didn't just use glue, they used thousands of tiny little wooden pegs.
This method has been called the sewn wood technique, which is such a perfect way to describe it. It wasn't just a chemical bond holding it together, it was a physical, mechanical interlock between all those layers. They were literally pinning or sewing the wood together.
So why go to all that trouble? Why not just use glue? Well, because they knew their environment. In the super dry climate of Egypt, animal glues could dry out, turn brittle, and eventually just fail. Those dowels were like an insurance policy, making sure the whole thing held together for centuries, even if the glue gave up. That is designing for the long haul.
And maybe the most amazing part of this whole story is that this ancient solution, well, it never really went away. Its core ideas have had this incredibly long legacy, and they're still fundamental to how we work with wood right now.
The Egyptians used this tech to make their precious resources go further. They'd use a super thin layer of that expensive imported cedar on the outside, the part everyone would see, while bulking up the inside with the cheaper, not so pretty local woods.
Does that sound at all familiar? It should. This is the exact same principle of veneering that's used in tons of furniture today. You know, a beautiful oak or walnut finish on the outside, hiding a core of less expensive material. The technique is basically identical. It's an ancient solution for efficiency that's still with us. Today, we're diving into the story of the very first synthetic plastic. And trust me, it's a fantastic one. Okay, so let's set the scene. We're in the early 20th century. Industry is booming, electricity is spreading everywhere, and with all that incredible expansion came a really desperate need for new and especially better materials. The biggest problem was insulation. You see, the whole electrical industry pretty much ran on shellac, which is a natural resin that comes from the lac beetle. But as you can imagine, as demand went through the roof, the supply just couldn't keep up. It was a huge bottleneck. The world needed a reliable synthetic replacement, and it needed it fast. And this is where our hero enters the picture. In 1907, a Belgian-American chemist named Leo Baekeland decides he is going to be the one to solve this shellac problem, once and for all. Now, Baekeland had a good idea of what chemicals to start with. The real issue was that he was up against a chemical reaction that was just famously wild. It was totally uncontrollable. So his challenge wasn't really about inventing something new from scratch. It was more about taming a beast that everyone already knew about.
You see, chemists at the time knew that if you mixed two chemicals, phenol and formaldehyde, and you added a little heat, you'd get this sticky resin. The problem was, the second you did that, you'd lose all control. The whole thing would just foam up like crazy and harden into this brittle, porous, and completely useless block. For pretty much everyone, it was a dead end.
So yeah, it wasn't some secret formula that was missing. It was just a notoriously difficult process, one that had stumped every single chemist who had tried to get a handle on it.
So how did Baekeland do it? How did he succeed where so many others had failed? Well, he didn't change the ingredients. Nope, he changed the process. He actually invented a way to control the chaos. And this was his stroke of genius, a machine he called the Bakeliter. It was basically a high-pressure chemical oven. By being able to precisely control not just the heat, but also the pressure, he could finally steer the reaction. He could even pause it halfway through to create a kind of moldable putty, which he could then cure permanently. He had finally tamed the beast. And the result of all this was the world's first fully synthetic thermosetting plastic. He called it Bakelite. Now the key here is the thermoset part. See, unlike a thermoplastic, which you can melt and reshape over and over, a thermoset undergoes a chemical change. It forms this permanent molecular structure once it's cured. You can't melt it again. It's like baking a cake. Once it's baked, you can't turn it back into batter. This made it incredibly heat resistant and, of course, a fantastic electrical insulator. So he had done it. He'd created a miracle material. But there was a catch, a really big one. The pure Bakelite resin, on its own, was almost perfect. I mean, it was heat resistant, it didn't react with chemicals, it didn't conduct electricity, but it was also unbelievably brittle. The slightest knock and it would just shatter into a million pieces.
So, to solve this very modern problem of his brittle plastic, Baekeland reached back, way back, thousands of years, for an ancient engineering solution. And this is where the story gets really cool.
This right here is the real heart of the innovation. For centuries, people have known that if you mix a binding agent or a matrix, like mud, with some kind of reinforcement, like straw, you get much stronger bricks. Baekeland applied that exact same principle. His modern matrix was the Bakelite resin and his reinforcement wood flour, which is basically just very, very fine sawdust.
Now, this wasn't just about mixing in some filler to make it cheaper. Not at all. The wood flour served a critical mechanical purpose. Each one of those tiny wood particles acted like a roadblock, what engineers call a crack arrestor. So when a tiny fracture would start to form in the brittle plastic, instead of spreading, it would immediately run into a particle of wood and stop dead in its tracks. The reinforcement absorbed the energy and kept the whole thing from falling apart.
So by combining his modern molecule with this ancient composite idea, Baekeland didn't just fix a flaw in his new material. Oh no, he unleashed a material that would literally go on to define an entire era.
And just like that, this new reinforced plastic was absolutely everywhere. It was strong, it was a great insulator, and you could mold it into all these complex, precise shapes. It became the go-to material for things like distributor caps in the brand new automobile engines, for the casings on telephones and radios, and just countless other parts that really pushed the modern world forward. And here is probably the biggest takeaway from all this. Backlund industrialized the composite. He took it from being a handcrafted thing, like an ancient bow that's made one at a time, and turned it into a standardized industrial commodity. You could follow a precise recipe and get consistent, reliable properties every single time.
Some of the biggest breakthroughs in history, they weren't planned at all. They were just happy accidents. And today we're diving into one of the absolute best, the story of how a simple lab mistake gave us a super material that completely changed the world, shaping everything from boats and cars to airplanes. So that's the big question, right? How on earth did a clumsy mistake in a lab create something stronger than steel and totally transform how we build, well, just about everything? Let's get into it. Okay, so to really get how big a deal this was, you gotta rewind the clock a bit. We need to look at what the world was like before fiberglass. See, engineers and inventors, they were always on this quest for the perfect material. And this really leaves out the problem they were up against. On one side, you've got your metals, like steel. Super strong for sure, but also super heavy. And, they rust. On the other side, you had these newfangled early plastics, like Blacklight. Totally revolutionary stuff, but let's be honest, they were pretty weak. They just didn't have the oomph for the really big jobs. What everyone was dreaming of was a material that could do it all. Lightweight, stronger than steel, and wouldn't rust. It was the holy grail. And that's where our story takes a sharp turn. Because the breakthrough didn't come from some grand, calculated plan. Nope. It happened because of a total 100% accident. All right, so let's set the scene. It's 1932. You're in the lab at the Owens, Illinois Glass Company. There's a researcher there, a guy named James Slater, and he's just doing his job trying to make these new glass building blocks. He's working with molten glass, pretty routine stuff for the time, nothing out of the ordinary. And then, whoops, a jet of compressed air suddenly hits the stream of molten glass. This was not supposed to happen. It was a complete mistake. And you'd think, well, there goes that batch of glass. But instead of a mess, something absolutely incredible happened. That blast of air literally atomized the liquid glass. It blew it into the shower of superfine, silky, continuous fibers. So this wasn't a failure at all. This was the light bulb moment. It was the accidental discovery of a way to mass-produce glass fiber. For the first time ever, they had a way to make tons of it, not just little decorative strands. And once that discovery was made, things took off like a rocket. I mean, for centuries, people had made little strands of glass for decoration, but it was just a novelty. After Slater's accident in 1932, it took just 6 years, for 2 huge glass companies to team up and form the Owens Corning Fiberglass Corporation. They weren't all in on this new material. Okay, so now they can make all these amazing glass fibers. Problem solved, right? Well, not quite. See, the fibers themselves were super strong, but they were floppy. They weren't a solid material on their own. They needed a partner, something to hold them all together, a kind of glue. They needed a plastic resin. And here's the roadblock. The resins they had back then were a real pain to work with. To get them to harden, you had to use tons of heat and incredible pressure. That meant you needed these huge, heavy, and really expensive steel molds. Think about it. You just can't make something big, like a boat hull or an airplane wing that way. It was totally impractical. So the glass fibers were ready to go, but their perfect dance partner hadn't shown up to the party yet. So what finally lit a fire under everyone to solve this problem? World War II. Suddenly, there was this desperate, urgent need for new materials for the war effort. They needed stuff that was lightweight but tough, and that wouldn't rust. For planes, for ships, for everything. Finding the right resin wasn't just a cool science project anymore. It was a top priority. And then, in 1942, it happened. The perfect marriage. You had Owens Corning, who had figured out how to weave all those glass fibers into this amazing flexible cloth. And at the exact same time, a company called American Siamed developed a brand new polyester resin they called Laminac. And this was the real game changer. Why? Because it could harden with just a little bit of heat and, get this, 0 pressure. That was the key. The 2 pieces of the puzzle finally clicked together. Now, this perfect marriage wasn't just about creating a new material. Oh no, it created a completely new way of making things. This was a full-on revolution that took manufacturing out of these giant, heavy industrial factories and put it right into the hands of regular people in their workshops. And the new process was so simple, it was genius. It was called the wet layup. You could literally take this soft, flexible glass cloth, drape it over a simple mold, any shape you want. Then you just paint on the liquid resin, saturating the cloth, and then you just wait. It hardens all by itself into this super rigid, super strong part. No giant presses, no crazy high temperatures. It was simple, it was cheap, and it was absolutely revolutionary. I mean, look at the difference here. Before, you needed heavy industrial presses and these crazy expensive machined steel molds. You had to be a giant corporation to even think about it. But after, no pressure needed. You could use a simple mold made out of wood or even plaster. Suddenly, making things was possible in a small workshop. This just blew the doors wide open for small inventors and entrepreneurs everywhere. And this quote just nails it. The process, it democratized composite manufacturing. That's the perfect word for it. It moved it from the heavy industrial press right down to the workshop floor. It literally gave the power to create these amazing things to pretty much anybody. So there you have it, the whole journey. A material that was literally born from an accident now had a process that put it in the hands of innovators all over the globe, and that unleashed a tidal wave of creativity that we are still riding today. I mean, think about it. From sleek sports cars to massive wind turbine blades, it all started with that one little oops moment in a lab. So, let's start with a little bit of a puzzle. I mean, think about it. What on earth could a humble, handmade sailboat from 1942 possibly have in common with one of the most advanced pieces of military hardware of its time? Well, the answer is a revolutionary material and a story of innovation that unfolded against all odds. The key to that puzzle, and this is where it gets really interesting, is found in two totally separate stories that were happening at the exact same time, right in the middle of World War II. On one side, you have an inventor driven by a simple passion for boating, and on the other, a team of scientists driven by the urgent life or death needs of a global war. Let's just paint a picture here. On one hand, you've got a garage in Ohio, a single inventor patiently tinkering away, just trying to build a better boat. On the other hand, a top-secret lab at MIT, where a team of brilliant scientists is racing against the clock to solve a problem that could help win the war. I mean, two completely different paths, right? But both were unknowingly walking toward the exact same discovery. Okay, let's kick things off in that quiet garage in Toledo, Ohio, where one man's personal project was about to start a revolution in how we make things. So, meet our first inventor, Ray Green. Now, this guy wasn't just some random tinkerer. He was an engineer. And get this, he'd actually worked for Owens Corning, the company that basically pioneered glass fiber. So he knew this stuff. He saw a potential in it that, frankly, almost nobody else did. So the year is 1942. Green gets his hands on two materials that were pretty cutting edge back then, a shipment of polyester resin and some glass fabric from his old contacts. His idea was, deceptively simple. Combine them and see if he could build a boat that was unlike anything else out there. And here's the part that just blows my mind. It wasn't just the boat itself, but how he made it. He didn't have a giant factory. Nope. He built a homemade autoclave. Think of it like a giant heater box right there in his garage to cure the material. And this single act proved you could create these incredibly strong, totally rot-proof and leak-proof structures without needing massive industrial machinery. He could mold these smooth, flowing shapes that were just impossible with wooden planks. Right there, in his garage, he had just invented the future of the entire marine industry. Okay, so let's hit pause on that quiet garage scene and jump into a completely different world. Because at the very same time Ray Green was building his boat, an urgent, top-secret project was kicking into high gear at the MIT Radiation Laboratory, better known as the Rad Lab. During the war, the Allies had a game-changing technology, radar. But there was a huge problem. The antennas were super fragile, and they had to be mounted on the outside of aircraft, where they were just getting hammered by 300-mile-per-hour winds, ice, and rain. They desperately needed a protective cover, something called a radome. And this created this massive engineering paradox. How do you build a shield that's strong enough to withstand all that abuse, yet is also completely transparent to radar waves. They needed a cover that was physically there, but electronically was like a ghost. I mean, looking at their options really shows what a jam they were in. Aluminum was strong, for sure, but it completely blocked the radar signal, a total non-starter. So they tried plywood, but it soaked up water, which blinded the radar system whenever a plane flew through a cloud. They were at a dead end. Until they landed on the exact same solution as Ray Green, a composite of glass fiber and polymer resin, GFRP. It was the perfect answer. It was strong, waterproof, and to a radio wave, it was like it wasn't even there. The Rad Lab scientists came up with this really ingenious design they called the A sandwich. It used two thin, strong skins of fiberglass, sandwiching a thick, lightweight core of either honeycomb or foam. This simple structure gave them an incredible amount of stiffness without much weight, and it minimized any reflection of the radar signal. It was just an elegant solution to a seemingly impossible problem. And right here, this is where the story of the boat builder and the story of the scientists finally converge, both proving the incredible power of this brand new composite material. And this wasn't just a theory. By 1944, these fiberglass radomes were standard equipment. They were fitted to the B-29 Superfortress, which let it do precision bombing right through the clouds, and on night fighters like the de Havilland Mosquito. These radomes were protecting the sensory organs of the Allied war machine, proving this material could perform under the most extreme conditions imaginable. And that's really the heart of our story. Two completely independent developments, one born from a desire for peaceful fun on the water, the other from the brutal necessities of war, had both arrived at the exact same solution. This wasn't just a wild coincidence. It was a powerful demonstration of how fundamentally versatile this material was. Glass fiber reinforced polymer could solve these wildly different problems because its core properties, strength, lightweight, and moldability, were just universally useful. So, with its power now proven in both civilian and military applications, the stage was set for a post-war explosion in design and manufacturing. The composite future had officially arrived. And the pace of adoption was just incredible. It all kicks off in 1942 with Green's first boat. Just 2 years later, in 44, fiberglass radomes are being used in active combat. By the 1950s, the marine industry that Ray Green had started was absolutely booming, changing recreational boating forever. A new era of consumer design had begun. And you better believe people noticed. The success in high-performance military craft and durable boats didn't go unnoticed. The automotive industry saw a chance to create radical new shapes that were impossible with steel. That lightweight, easily molded body of the iconic Chevrolet Corvette, for instance, made possible by this very same fiberglass technology. And that ability to create these flowing, organic shapes wasn't just for cars. It transformed furniture design. Designers Charles and Ray Eames embraced the material to create their famous molded chairs, bringing modern forms that actually hugged the human body into homes for the very first time. And to bring the story full circle right back to recreation, it revolutionized sports. The modern surfboard, strong, lightweight, and super responsive, is a direct descendant of the work done in that Ohio garage and that top-secret MIT lab.
All right, today we're jumping into the story of advanced composites. You know, they're kind of the unsung heroes of modern engineering. They are literally hiding in plain sight, in everything from the planes we fly in to the giant wind turbines that are powering our future. So let's get into it.
So to kick things off, I've got a question for you. What on earth could Thomas Edison's first working light bulb have in common with a super advanced jetliner like the Boeing 787? I mean, they're worlds apart, right? Separated by more than a century of incredible technology.
Well, the answer is a fascinating story about a piece of technology that was completely forgotten and then resurrected to solve a massive, massive problem. A problem that was honestly pushing engineering to its absolute breaking point.
And that massive problem? It has a name. The weight wall.
This was the fundamental challenge that engineers in the mid-20th century kept smashing into. The frustrating reality that every time they made something stronger, it inevitably got heavier.
See, back in the 1950s, the go-to materials were metals. Steel, aluminum, and they were great, strong, stiff, pretty reliable. But they had two huge problems. First, they were heavy. And second, their strength was what you call isotropic. That just means they were equally strong in all directions. Now, that sounds like a good thing, but it's actually super inefficient. The new era of jets and rockets, though, it needed the impossible. Materials that were way stronger, radically lighter, and this is key, could have their strength targeted only where it was needed most.
And the scale of these challenges was just immense. We're talking about preventing things like aeroelastic flutter, which is a terrifying thing where a plane's wings can start flapping uncontrollably and literally tear themselves apart at high speeds. They needed rockets that could handle the incredible stress of launch and missile warheads that could survive the blistering heat of re-entering the atmosphere. Your basic metals just couldn't do it all without adding so much weight that a plane couldn't carry any cargo or a rocket couldn't even get off the launch pad.
So you're an engineer. You're faced with this weight wall. What do? You have to think completely differently. And this led to a total reimagining of what a material could be, based on a principle that created something way, way stronger than the sum of its parts.
And this is it, the advanced composite. Now, it's not just one material. Think of it more like a team. You have these incredibly strong, high-performance fibers, carbon fibers, the famous one, and they provide all the stiffness and strength. Then you embed those fibers in what's called a matrix material, like a resin, which does the crucial job of holding them all together, protecting them, and spreading the load out between them.
So the key idea here, the real magic, is synergy. On their own, the fibers are super strong, but they're brittle. The matrix is kind of weak, but it's tough. But when you combine them, you get a brand new material that has the best qualities of both. It's that classic case where 1 + 1 suddenly equals 3. This is the absolute game changer. Unlike a chunk of metal, with a composite you can actually lay down the fibers so they're oriented to provide strength precisely where the stress is going to be highest. This is called tailored anisotropy. It means you're not wasting a single ounce of material adding strength where you don't need it. It is the ultimate in engineering efficiency.
But hang on, where did this whole idea of using super strong carbon fibers even come from? Well, this is where our story takes that really unexpected turn, all the way back to that light bulb we mentioned at the start. This is a pretty wild origin story. It turns out that back in 1879, in his obsessive quest to find a long-lasting light bulb, Thomas Edison was basically baking everything he could get his hands on, cotton threads, bamboo slivers, at really high temperatures without any oxygen. This process, called pyrolysis, cooked off everything except the carbon, leaving behind the world's very first carbon filaments. He had no idea, but he had just created the direct ancestor of modern carbon fiber.
But here's the thing. Edison's fibers were really brittle and weak. And as soon as stronger tungsten filaments were invented for light bulbs, carbon was completely tossed aside. It was rendered obsolete. For more than 50 years, the idea of a carbon fiber was nothing more than a historical footnote, a dormant technology just waiting for the right problem to come along. So how did this forgotten idea make such a huge comeback? Well, in the middle of the 20th century, two completely different forces came together and created a perfect storm, bringing Edison's lost idea roaring back to life.
The first force was pure science. Back in the 1920s, a scientist named A.A. Griffith had this brilliant insight into why things break. He figured out that all materials, no matter how solid they seem, have tiny, microscopic flaws in them. And it's these little flaws that act as stress concentrators and cause the material to fail.
This discovery, of course, leads to a critical question. If these tiny flaws are the enemy of strength, how do you get rid of them? Or, how do you at least dramatically lower the chances of a big one existing?
And the answer is surprisingly elegant. You make the material incredibly thin. When you pull a material down into a fiber that's just a few microns thick, the statistical probability of it containing a major, strength-limiting flaw drops to almost zero. This means the fiber's strength can get mind-bogglingly close to the theoretical limit of its own atomic bonds. So, Griffith's theory gave us the scientific why.
The second force was a desperate, urgent need.
We're talking about the Cold War and the race to develop intercontinental ballistic missiles, ICBMs. This created an extreme engineering challenge that the US military poured everything into solving. They needed materials that could perform under conditions that, frankly, had never been seen before.
Just look at that number, 5,000 degrees Fahrenheit. Let that sink in. That is hotter than the melting point of most metals. And it's the kind of insane heat a missile warhead had to survive as it screamed back into the Earth's atmosphere at thousands of miles an hour.
The problem was terrifyingly simple. No conventional metal alloy could survive that kind of temperature. Even the early composites they had, like fiberglass, would just melt away or fail completely. A new material wasn't just a nice to have, it was an absolute necessity for national security.
And so, right there, the theoretical potential of carbon fibers finally slammed into the urgent demand from the military. This incredible convergence kicked off what we now call the composite age, and it's what took these materials from top-secret projects to the planes we all fly in today.
The really crucial thing to understand here is that the Cold War acted as the perfect, if incredibly intense, incubator for this tech. This was a race where performance was the only thing that mattered. Cost? That was a secondary concern, which basically gave scientists and engineers a blank check to push the boundaries of what was possible.
And just look at the result. That massive investment paid off in ways no one could have possibly predicted. The exact same kind of technology developed for those missile nose cones is now used to build the main body of the Boeing 787, making it way lighter and more fuel efficient. It's in giant wind turbine blades, high-performance cars, it's everywhere.
All right, so let's talk about one of the most incredible materials ever invented. It's the backbone of stealth fighters, it's in our supercars, and what's wild is that, by all rights, it really shouldn't even exist.
Okay, so let's dive into part 1, the impossible fiber. Our story kicks off right at the beginning, with a discovery that was, well, both a miracle and kind of a complete dead end.
So, back in the 1950s, the whole idea of a perfect carbon fiber was just so out there. It was pure science fiction. In fact, the engineers working on it had this nickname for it, unobtainium. They knew it was theoretically possible, but actually making it? Yeah, that felt like trying to grab smoke.
And then in 1958, it just happened, completely by accident. A physicist, Dr. Roger Bacon at Union Carbide, wasn't even trying to invent some new wonder material. Nope. He was doing some really fundamental research on the triple point of carbon when he noticed these incredible, tiny, perfect graphite crystals, or whiskers, forming in his furnace.
And when they tested these things, wow, their properties were just staggering. We're talking a tensile strength of 20 gigapascals. To put that in perspective, this was, hands down, the strongest and stiffest material for its weight that humans had ever created.
But, and there's always a but, right? There was a huge problem. These perfect little crystals were microscopically small, and making them, oh boy, the cost was estimated to be in the millions of dollars per pound. So science had proved the dream was real, but engineering just couldn't make it happen. The material was still, per all practical purposes, unobtainium.
So, this brings us to our next chapter, a dream shattered. Obviously, researchers had to find a more practical way to do this, and for a little while, it really looked like they'd cracked the code. But what they were actually doing was setting the stage for one of the biggest, most public engineering disasters of the entire century.
Okay, so over in the UK, some clever folks figured out a new way to make carbon fiber that was actually practical. And the legendary company Rolls-Royce? They saw this and bet the entire farm on it. They decided to build the fan blades for their revolutionary new jet engine, the RB2101, out of this new carbon fiber composite.
Now, this was a huge deal. Lighter blades meant a lighter engine, which meant massive fuel savings. The whole company's future was riding on this. But it all came down to one single, brutal test. Could these new carbon fiber fan blades survive a bird strike at takeoff speed?
The answer was a catastrophic no. They couldn't. The fibers, while super stiff, were also brittle. They just shattered. The engine was completely destroyed. The failure was so total, so public, and so expensive that it actually forced Rolls-Royce into bankruptcy in 1971. Just like that, the dream was shattered. And carbon fiber? It was now seen as this dangerous, unreliable joke.
All right, part 3, the boron bridge. Now, with carbon fiber's reputation in absolute tatters, you'd think that's it, right? Game over. But the US military had a serious problem. A problem that only an advanced composite material could solve. So they turned to a rival material to, well, build a bridge to the future.
See, the Cold War and Vietnam were pushing aircraft to their absolute limits. You had these new swing-wing jets like the F-111 and fighters like the F-14 Tomcat, and they were facing such immense structural loads that their metal tails were literally at risk of being torn apart by something called aeroelastic flutter. They needed something way stiffer and lighter than metal, and they needed it yesterday.
So, with carbon fiber tainted by that Rolls-Royce failure, they turned to boron. Boron fiber was really the first successful advanced composite. It was incredibly stiff, and it was tough.
It became this crucial bridge technology for the tails on the F-14 and the F-15. But, and here's the catch, it was a real pain to work with. The fibers were thick, hard to shape, and you needed expensive diamond tools just to machine the stuff.
So that brings us to its big comeback, redemption in the skies. While boron was the go-to material, the disgraced carbon fiber was quietly getting a second chance, kind of maturing in the background, away from the spotlight.
You see, all through the 1970s, the process for making carbon fiber just kept improving. Costs, which were once astronomical, started to come down. The fibers themselves got thinner, more flexible, way easier to work with than that clunky boron. So by the time the next generation of jets came around, we're talking the F-16 and the F-A-18, carbon fiber was suddenly the obvious choice. It had finally arrived.
And for about 2 decades, the growth was fueled by this Cold War mentality of performance at any cost. The entire carbon fiber industry was basically a supplier for the Department of Defense. The only thing that mattered was making the best possible fighter jet, and cost was, well, it was a secondary concern. This led to a huge expansion of production capacity, all built on this one assumption, that the Cold War would last forever.
Which brings us to part 5, the peace dividend crash. This is the second near-death experience for carbon fiber, when the world, and the industry's entire business model, changed almost overnight.
It happens so fast. In 1989, the Berlin Wall falls. By 1991, the Soviet Union collapses. The Cold War, the entire reason this massive performance-at-any-cost industry even existed, was just over. Major aerospace programs were getting canceled or scaled way back. And you can guess what that meant. The effect on the carbon fiber industry was immediate and absolutely catastrophic. Its one, and really its only major customer, was practically vanishing before its eyes. Just look at this number. In the span of a single year, usage by the Department of Defense dropped by 60%. 60! The entire industry was on the brink of collapse. It had all this capacity to build materials for a war that just wasn't being fought anymore.
So here we are again. The industry is on the brink of total collapse. The technology was finally mature, it was amazing, but its entire market had just, poof, evaporated. So what do? Where could a material designed for warheads and fighter jets possibly find a new customer?
Which brings us to our final and maybe most surprising chapter, saved by sporting goods. Yeah, you heard that right. This military-grade, high-tech material found its salvation in the most unlikely place imaginable.
The new market wasn't in aerospace. It wasn't in supercars, not yet anyway. It was in things like golf club shafts, tennis rackets, and fishing rods. To survive, the industry had to pivot, and pivot hard. The very same fibers designed for the skin of a fighter jet were now being used to help someone hit a golf ball a few yards farther.
And this pivot, this move into consumer goods, became the industry's lifeblood. It was nowhere near as glamorous as building stealth bombers for sure, but it provided the cash flow to keep the lights on, to keep the factories running, and to keep funding R&D. It literally laid the groundwork for all the future uses we see today.
Welcome to The Explainer. You know, today we're going to unravel the story of a material that honestly should never have existed. It was born from a total mistake, a failed experiment that somehow ended up changing the world. It's a fantastic story about how one scientist's intuition completely trumps standard procedure.
All right, our story actually begins not up in the sky, but right down here on the ground. It's 1965, and there's a potential gasoline shortage looming. So the auto industry has this really practical problem. They desperately need a stronger, lighter fiber to make better car tires.
So over at DuPont's pioneering lab, a chemist named Stephanie Kwolek gets this assignment. She's experimenting with this specific class of materials called rigid rod polymers, and her job is to engineer the perfect solution for this tire problem.
Okay, and this is where the story takes a really fascinating turn. The search for a better tire is about to go from a totally routine experiment to a legendary discovery. And it all happened because something went completely wrong.
By every single standard of the day, this result just screamed failure. The liquid she created was cloudy, kind of pearly looking, and watery thin. I mean, the exact opposite of what she was hoping for.
The rule book on this was crystal clear. A solution that looked like this, it was considered contaminated, or maybe it just didn't polymerize correctly. Basically, it was junk. Standard operating procedure was simple. You throw it in the trash, and you start all over again. But this is where Stephanie Kwolek's scientific curiosity just took over. She had a hunch. Something about this supposedly useless liquid just felt different. So she insisted she really had to push past the normal protocol to get them to spin it into a fiber. And that one decision? Well, it was about to change material science forever.
So let's see how this gut feeling led to a truly world-changing material. Because the result of her persistence wasn't just interesting, it was absolutely mind-blowing.
The fiber that came out of that failed solution was just startlingly strong. When they finally tested it, they found out it had a tensile strength 5 times that of steel on a weight-for-weight basis. Just think about that for a second. 5 times stronger.
Now, the crucial thing to understand is that this incredible strength came from its unique internal structure. See, the long, rigid polymer chains inside were perfectly aligned, almost like a bundle of uncooked spaghetti. This perfect alignment allowed them to act like billions of microscopic reinforcing rods, all pointing in the same direction, which gave the fiber its unbelievable strength.
As you can imagine, DuPont quickly trademarked this revolutionary new material. They called it Kevlar. And while most of us know it today for stopping bullets in body armor, its most profound and life-saving impact would actually be found thousands of feet up in the air. And that brings us to its defining application in aerospace, solving a violent and potentially catastrophic problem that can happen deep inside a jet engine.
So here's the problem. It's called a blade-out event. If a massive fan blade detaches while it's spinning at incredible speeds, it releases an enormous amount of energy. Enough to act like a cannonball, basically, and pierce right through the engine casing and even the body of the aircraft. So the challenge was, how do you stop it without adding a ton of weight?
And here's the genius of the new solution. I mean, think about it. The old way, you'd use this massive, incredibly heavy steel ring to contain the blast, but the new way, it's just a wrap of this dry Kevlar fabric. It's so much lighter, and it approaches the whole problem from a totally different angle.
Instead of just acting like a steel wall to block the blade, the Kevlar wrap works more like a catcher's mitt. When that high-speed blade hits it, the fabric deforms and stretches, and it safely absorbs all that immense kinetic energy through fiber strain and friction. It just catches it and stops it from ever reaching the main body of the plane.
But Kevlar's impact didn't just stop at the engines. It also became this silent, unseen guardian inside the aircraft's main body, protecting it from the inside out. So the walls of an airplane's cargo holder lined with Kevlar laminates. Now they have to withstand all kinds of abuse from luggage and equipment, but more importantly, they provide this tough, puncture-resistant and even fire-resistant barrier that protects the plane's essential structure. It can even contain a fire long enough for the plane to land safely. It's really a powerful reminder, isn't it? A material that was born from a mistake, from a solution that was supposed to be thrown away, became an absolutely essential yet completely unseen component of modern air travel safety.
All right, today we're going to dive into a story about materials science getting pushed to its absolute crazy limit. We're talking about creating materials that can actually thrive in places so hot they could turn solid steel into soup.
So, how do you build for temperatures that can literally melt metal? I mean, this isn't just some abstract question, it's what drove decades of incredible innovation. Think about jet engines or hypersonic vehicles. You're not just dealing with a little bit of heat, you're facing a literal wall of fire. So how on earth did engineers manage to conquer it?
Okay, to really get a handle on the solutions, we've got to first appreciate just how big this problem was. And it all starts with the very first generation of those famous composite materials.
You know, materials like carbon fiber and Kevlar, they're famous, right? They completely revolutionized everything from our tennis rackets to body armor because they're so incredibly strong and light. But they had this one critical weakness. It all came down to the polymer resin, basically the glue that holds all those strong fibers together. See, that polymer glue starts to break down at temperatures above, say, 150 to 200 degrees Celsius. Now, that might sound hot, but for the most demanding parts of a plane or a spacecraft, we're talking engine exhausts, the nose cones of hypersonic craft, that's just not even close to hot enough. So engineers needed something way, way tougher.
And that search for something tougher, is what led to our first family of these incredible fire-mastering materials, metal matrix composites, or MMCs for short.
The idea behind MMCs is actually brilliantly simple when you think about it. Instead of using that polymer glue that melts, what if you just took those super strong fibers and embedded them inside a metal matrix, like aluminum or titanium?
All of a sudden, you've got this new hybrid material that can handle way higher temperatures.
And what's so cool is that this approach really does give you the best of both worlds. You get to keep all the good stuff from the metal, its ability to handle heat and bend without snapping, but then you infuse it with the absolutely mind-blowing stiffness and strength of the fibers. The result? A true super material.
Okay, let's talk about a classic example, the Space Shuttle Orbiter. The main body of the shuttle, the fuselage that went around that huge payload day, had some really tough requirements. It needed to be ridiculously light, super stiff, and stay stable even when temperatures swung wildly. So what did they do? They used these special tubes made of boron fibers embedded in an aluminum matrix. And the result was incredible. They saved 320 pounds. That's a 44% weight reduction from what they originally planned. And in spaceflight, where every single pound is critical, that wasn't just a small improvement, it was a massive victory.
But MMCs weren't just about saving weight. They were also amazing at solving some really dangerous engineering problems. Let's take the F-16 Fighting Falcon. In its early days, this jet had a huge issue. These two little fins under its tail would vibrate so violently it was becoming a real problem.
I mean, the original aluminum fins were literally shaking themselves to pieces, failing after only a few hundred hours in the air. Now, instead of doing a whole costly redesign of the jet's aerodynamics, the engineers did something much smarter. They just swapped out the material for a stiffer MMC, and check out the result. The service life went from just hundreds of hours to thousands. Just like that. Problem solved.
But even with all these successes, MMCs had their limits. And engineers were about to come face to face with an environment so unbelievably extreme, it made all these other challenges look like a walk in the park.
Welcome to the inside of a modern jet engine. I mean, this is the final frontier of heat. We're talking temperatures that soar past 1300 degrees Celsius. That is way, way beyond the melting point of the metals used in those MMCs. There's really only one type of material that has a prayer of surviving in here: ceramics.
But that brings up a huge, potentially catastrophic problem. You see, while ceramics can definitely take the heat, they are famous for being brittle. Think about it. A bird strike, or even just a sudden temperature change, could cause a ceramic part to shatter, just like a dinner plate. And in a jet engine, that means total, catastrophic failure.
So this incredible challenge led to the next big evolution in materials: ceramic matrix composites, or CMCs. But the idea of making a tough, reliable engine part out of something as brittle as ceramic? Well, let's just say it was met with intense skepticism.
And this quote right here, it just says it all. Back in 2001, a major defense report literally asked, "Will pigs fly before ceramics do?" That's how impossible it seemed. All the experts thought the cost to make them was just way too high, and that risk of them shattering was simply a deal breaker.
But you know what? They were wrong. A team at General Electric spent decades and billions of dollars proving it, and they finally succeeded thanks to this incredibly clever mechanism called crack bridging. This was the breakthrough that finally made CMCs a reality.
So, how does this magic actually work?
Well, imagine a tiny microscopic crack starts to form in the brittle ceramic part. Instead of shattering, the super strong ceramic fibers woven inside act like microscopic rebar. They literally bridge that tiny gap, holding the whole thing together. This means the part can keep carrying its load even after it's been damaged, giving it this amazing property, a sort of pseudo-ductility. It can bend and flex in a way that normal ceramics just can't.
And this breakthrough wasn't just some cool thing they figured out in a lab. No, it completely changed the game for how we design jet engines.
So where did they first show up? Well, the big commercial debut for CMCs was inside the high-pressure turbine of the CFM LEAP engine. And that's the engine that powers a lot of the Airbus A320neos and Boeing 737 MAX jets that are flying all over the world right now.
And the benefits? They were absolutely staggering. First, because CMCs can handle so much more heat, they don't need all those complex little channels for cooling air that the metal parts used to need. That saves a ton of weight. But even more important, it means you don't have to bleed as much air away from the engine's core just to cool parts down, and that makes the entire engine run more efficiently.
Get this, the CMC components in that LEAP engine weigh just 1/3 of what the old metal superalloys did. A 2/3 weight reduction in one of the hottest, most critical parts of the engine, that's not just an improvement, that is revolutionary.
And the incredible success in the LEAP engine? That was just the beginning. It proved the technology worked, and that paved the way for CMCs to be used in even bigger, next-generation engines,
like the massive GE9X. It turns out the pigs had finally learned to fly.
There is really no better symbol than the Boeing 787 Dreamliner. I mean, this plane is the moment carbon fiber went from being this exotic, niche material to becoming the absolute gold standard in aviation.
Just take a look at this. The Dreamliner is 50% composite materials by weight. We're not talking about a few fairings or panels here and there. No. This is the primary structure, the fuselage, the wings, the whole shebang. This is what the industrial maturity of a revolution looks like.
And this right here, this slide just perfectly lays out how composites changed everything. See, the old way was all about riveting together countless sheets of aluminum. But with the 787, Boeing built entire sections of the fuselage as single, seamless carbon fiber barrels. It was a brilliant move. It got rid of thousands of fasteners, which cut down assembly time and, this is the big one, it seriously reduced aerodynamic drag.
And the payoff for all that sleek, lightweight design? A massive 20% improvement in fuel efficiency compared to the old 767 it replaced. In the airline world, that is a gigantic leap forward, a huge win for their bottom line, and of course, for the environment.
But hey, the benefits weren't just for the airlines. They were for you, the passenger. Because composites don't rust or corrode like metal, Boeing could keep the cabin air more humid. They could also pressurize the plane to a more comfortable 6,000 feet of altitude instead of the typical 8,000. So what does that actually mean for you? Well, it means you step off a long flight feeling way less tired and dehydrated. It's a game changer.
And check this out. This just perfectly shows you how durable this stuff is. After years and years of service, flying all over the world, the maintenance data is crystal clear. Zero fatigue issues. Think about that for a second. It's a total paradigm shift from the old days of metal planes, where engineers were in a constant battle against metal fatigue.
So, okay, composites totally conquered the skies. They won. But the next question was pretty obvious. How do we make these incredible materials even better? And the answer, as it turns out, was to start thinking really, really small.
All right, this is where things get really wild. We're leaving the world of big airplane parts and diving into the nanoscale, where scientists are unlocking properties that honestly sound like they're straight out of a sci-fi movie.
So, what exactly are we talking about here? What are nanocomposites? Well, think of it like this. You take a conventional composite, like carbon fiber, and you supercharge it. You infuse it with these microscopic particles, things like carbon nanotubes or graphene, and suddenly it can do all sorts of extraordinary new things.
And when I say extraordinary, I am not kidding. Get this. Researchers found that by adding a teeny tiny amount of graphene, we're talking just 0.075% of the total weight, they could boost the strength of a carbon fiber by 225%. That's a mind-blowing improvement from a practically invisible amount of material.
Okay, so that's the theory, but how does this stuff actually work in the real world? Well, let's take a look at NASA's Juno spacecraft, which flew to Jupiter. It had to survive these insane radiation belts that can build up static electricity, little sparks that can completely fry a spacecraft's sensitive electronics. Now, the old school solution would have been to wrap everything in heavy aluminum foil for shielding. But the new way? Juno's skin was built from a composite material that was infused with carbon nanotubes. These tiny tubes created a conductive web right inside the structure itself, safely getting rid of any static charge. No extra weight, no metal foil. Just a perfect, elegant solution. And we see this same kind of thinking in military tech, especially with the F-35 fighter jet. Older stealth planes like the B-2 bomber had to be covered in these fragile, high-maintenance coatings that absorbed radar signals. The F-35, on the other hand, builds its stealthiness right into its skin using nanocomposites. It's not a delicate coating, it's part of the plane itself, which makes it way more durable and ready for action.
All right, so everything sounds amazing, right? Lighter planes, deep space missions, stealth fighters. But this incredible success story has a flip side, and it's a big one. The very chemistry that makes these materials so tough and long-lasting also creates a huge environmental headache when they reach the end of their life.
So here's the core of the problem. Most of these super strong composites are what you call thermosets. It means you mix the fibers and the resin together, and then you cure it with heat. It's kind of like baking a cake. That heat creates a chemical bond that's irreversible. You can't just melt the cake back down into batter, and you can't melt these composites down to reuse them like you can with metal. Once it's made, it is made for good.
For a long time, for good just meant it ended up in a landfill.
but that's starting to change. Now, the industry is in a race against time, trying to find clever new ways to close that loop and create a truly circular future for these incredibly valuable materials.
And really, the effort is splitting into two main camps. First, you have people trying to figure out what to do with the mountains of composite waste we already have. And second, you have designers trying to create totally new, green composites from scratch that are built to be sustainable right from the start.
So on the recycling side, you have companies like ELG Carbon Fiber doing some really clever stuff. They take manufacturing scrap, like the leftover bits from making a 777 X-Wing, and they cook it in a special oven without any oxygen. This process is called pyrolysis, and it basically burns off all the resin but leaves the super valuable carbon fibers behind. Those reclaimed fibers then get sold to other industries, like car parts or electronics. It literally turns trash into treasure.
Then you've got the second approach, which is all about designing smarter from the very beginning. Boeing's Eco Demonstrator program, for instance, has been testing out panels for inside the cabin made from flax fibers. Yep, a plant, mixed with bioresins. It turns out flax is amazing at damping vibrations, which is perfect for making the cabin quieter. And of course, using renewable materials like that slashes the carbon footprint over the product's whole life.
So is any of this actually working? Absolutely. These recycling partnerships have already saved millions of pounds of high-value carbon fiber from ever seeing a landfill. It's a huge, huge step in the right direction.
You know, we've been promised flying cars for, decades now? It's the classic image of the future. But it turns out the key to finally making them a reality wasn't some crazy new engine or a super battery. Nope. It was a revolution in the very materials they're built from. Today, we're going to dive into the thermoplastic revolution and see how it's finally unlocking the dream of personal air travel. So that's the big question, right? Are flying cars finally here? And the answer is, well, almost. But they're not really cars in the way we think of them. The industry has a much cooler name for it: urban air mobility, or UAM. Just picture thousands of electric vertical takeoff and landing aircraft, basically air taxis, zipping people across cities. And when I say thousands, I mean it. The vision here is absolutely massive. Companies you might have heard of, like Joby Aviation and Archer Aviation, they aren't aiming to build a few hundred of these a year like we do with traditional airplanes. They're talking about manufacturing on a scale that looks a whole lot more like the car industry. But that incredible ambition smacks right into a huge, huge problem. And that brings us right to the heart of the matter. This is the great production problem. How on earth do you build something with the safety and precision of an aircraft, but at the speed and scale of a car? The old ways of doing things, they just won't cut it. Not even close. Think about it like this. Traditional aerospace has always been about low volume and a super slow, meticulous pace. Building a modern jetliner takes forever. And that's okay, because you're only building a few of them. But UAM needs the exact opposite. It needs high volume, and it needs to be fast. You just can't use a 20th century manufacturing process to build a 21st century transportation network. And the real bottleneck? Well, it's in the material itself. For decades, the go-to material for anything that flies has been something called thermoset composites. And they're amazing. They're incredibly strong and super lightweight, perfect for an airplane. But they have a fatal flaw when it comes to mass production. Once you get them into the shape you want, you have to bake them, literally, for hours in a giant high-pressure oven called an autoclave, just to get them to harden permanently. And I'm not exaggerating. We're talking hours for just one single part. Now just try to imagine building thousands of air taxis a year when every major piece of the fuselage, every wing, every door, has to spend hours sitting in an oven. It's an impossible bottleneck. You just can't get to automotive speeds with a process that takes that long. It's a total non-starter. But what if you could change the material? What if there was a better way? Well, this is where the hero of our story comes in. Let's talk about the thermoplastic revolution. Okay, so here's the breakthrough, and it's a huge one. Think of a thermoset like baking a cake. Once you mix the ingredients and put it in the oven, it undergoes a chemical change. You can't turn that cake back into batter, right? It's a one-way street. But thermoplastics, they're more like ice. You can melt ice into water, and then you can freeze it right back into ice, over and over again. That simple ability to be melted, reshaped, and re-solidified, that changes everything. And the difference this makes in the factory is just night and day. First, manufacturing time. The cycle time drops from hours down to mere minutes. Second, the material is reusable, which is a massive win for cutting costs and for sustainability. And maybe the coolest part, assembly. You can actually weld thermoplastic parts together just like you would with metal. That means you can get rid of thousands of heavy rivets and messy, complicated adhesives. It's a total game changer. So the new process is just beautifully simple and unbelievably fast. You take a sheet of this thermoplastic composite using advanced polymers like PEEK. You heat it up until it's pliable, you stamp it into shape in a mold, which takes minutes, and then you weld the finished parts together. Heat, stamp, weld. It is a complete paradigm shift. And the benefits just keep on stacking up. Thermoplastics aren't just faster, they're also naturally tougher and more resistant to impacts than the older, more brittle composites. By getting rid of all those rivets and glues, you make the aircraft lighter, which is always good, and you make putting the whole thing together at the end way, way faster. So you see, this isn't just a story about a new kind of plastic. This is about how a fundamental breakthrough in material science is the key that unlocks an entirely new vision for mass transportation. There's a quote from industry experts that just says it all perfectly. Aerospace-grade structures at automotive speeds. That one phrase, that is the holy grail. It captures the exact breakthrough, the exact miracle that's needed to make this vision of thousands of air taxis a real, plausible future. And listen, this isn't just theory or something happening in a lab. This is happening right now. Look at who's involved. Joby Aviation has partnered up with Toray, a giant in advanced composites. Archer Aviation is working with Hexel and FAC. These are major players building a real supply chain to make high-rate production happen. So what does all this technology, all these partnerships, what does it all lead to? Well, it enables something people are calling the democratization of flight. That's a powerful phrase, isn't it? It means moving from a world where flying is for long distances or special occasions to one where it could be an everyday choice for just getting across town. Now, to really appreciate how big a deal this moment is, it really helps to zoom out and see where it fits in the whole history of advanced materials. It's been quite a journey. You know, the age of advanced composites really kicked off because of the desperate needs of the Cold War. We got things like carbon fiber out of that. Then, in the 70s, we entered an age of resilience with incredible materials like Kevlar. Today, we're smack in the middle of the age of processability, driven by this UAM revolution and the desperate need for speed. And believe it or not, the next era is already coming into view. Because the journey doesn't stop here. The future of these amazing materials isn't just about making them stronger or faster to produce. The next great challenge, the next frontier, is sustainability. Creating composites that are just as revolutionary, but are also recyclable and maybe even derived from biological sources. So if you take just one thing away from our explainer today, let it be this. The flying taxi revolution isn't really about slick new aircraft designs or better batteries. At its very core, it is a revolution in materials science. The vehicle of the future is literally being born from the material of the future. And that leaves us with one final big thought to chew on. We've seen how this completely changes the game for aerospace, but what happens when you can create incredibly strong, ridiculously lightweight structures not in hours, but in minutes? What other industries, from cars to construction, medical devices to consumer goods, are about to be completely and utterly transformed?